what we're going through in this part and building from here is looking at those electrons and what kind of an ordered pattern those electrons are in. Because when you take two atoms and bring them together, it's the electrons that make contact. And so it's the electrons that control reaction. And electrons react the way they do based on the way they're arranged. So we're looking at today how the electrons are arranged. And as we go on over the next several classes, we'll look at how the electrons are arranged affects behavior of the elements. And then how the behavior of the elements affects formation of compounds, and how the formation of compounds affects their shape, and how their shape affects things like whether they're soluble in water or not. And so it's a very conceptual, but very much building set of material over the next few weeks. Right? So, and it all starts with this. So, Study Pack 2, first page, is going over the directions of what that layered system is like. And there's all kinds of analogies to help conceptually with this, and a few of those we'll talk about. But fundamentally what it comes down to is what you've got listed here with the four arrowed points. Is that out from the nucleus, you've got electrons existing in various energy levels. There are certain distances from the nucleus where electrons can maintain stable orbit. The analogy would be like the planets, or like, I guess like satellites around the Earth would be a better example. Because there's a certain distance that NASA always puts their satellites. Because at that distance out, they'll maintain a stable orbit. If they're not that far out, they come crashing back to Earth. If they put them too far away from the planet, they drift off into space. But there's a certain distance where the satellite can maintain orbit. And if you compare that to the planets, there's certain distances where you can go out and go find a planet, and other distances you don't. It's that kind of a thing. It's not a orbit like a planet pattern, but you do have an element of stability there. And so each of these levels, starting the one closest to the nucleus, they're numbered counting outward. The one closest to the nucleus is level 1, then 2, 3, 4, etc. That's shown in the diagram at the bottom of the page as energy levels counting upward. Each level is split into sublevels, and these are given letter designations of S, P, D, and F. If it were up to me, there would have been A, B, C, and D. That would be a whole lot easier to remember. But it is what it is. S, P, D, F is the order for those. And just like 1, 2, 3, 4 is increasing energy, going from S to P to D to F, that's increasing energy. Each level consists of sublevels. Level 1 has only one sublevel, and so that would be the 1S. Level 2 has 2 sublevels, that would be S and P. Level 3 has 3 parts, S and P and D, and so forth. So as you get further from the nucleus, you've got more and more sublevels and the ability to contain more and more electrons. Each sublevel is split into what's considered orbitals. Orbital is defined as a region in space where it's likely you'll find an electron. we don't really technically have orbits, because an orbit is a very predefined pattern. With the Earth going around the sun, we know exactly where it's going to be on any given day of the year, predicted out into the future, because it's a very predictable pattern. That's an orbit. Electrons don't orbit in that sense. What you have is this orbital, which is a region of space. Maybe it's a spherical region of space. Some of them are more of a figure-8 shape as that region of space. But what you have in that region of space is electrons moving around randomly, but they stay in that region. Do you see the difference between an orbit and an orbital? If you've got a horse in the field, the horse does not go around the perimeter of the fence indefinitely, correct? But you know he's in that field somewhere. That would be the analogy, I guess. Orbitals, S sublevels are a single orbital. So on the diagram, that little line, each of these little lines represents an orbital. S orbitals are always single orbitals. S is always single orbital. But P's come in groups of 3. D's are always in groups of 5. And I've run out of room here, but F's are in groups of 7. And that's on your diagram anyhow. But that's the layered structure. Levels are composed of sublevels, sublevels are composed of orbitals. And electrons wander around within those orbitals. And the criteria there are, first, they want to get as close to the nucleus as they can because that's opposite charge attraction. Negatives are attracted to positives. And so the electrons will be in the lowest energy orbital that they can be, because that's as close to the nucleus as they can get. And all orbitals max out at 2 electrons, regardless of the type. All individual orbitals fill at 2 electrons. They could be empty, they could have 1, they could have 2, but that's it. You cannot have ever more than 2 electrons per orbit. Now, we're going to be looking at what's called electron configuration. The diagram here is the same as it was on the previous page. And we're going to use that diagram to predict what's called electron configuration which is a shorthand inventory telling where each electron is. And the information and configuration is the level, the sublevel, and then as a superscript, the number of electrons in that sublevel. So what we're going to do is take a bunch of elements, we're going to diagram them according to that chart, but then summarize that chart in what's called electron configuration. And notice that chart gives you level, sublevel, and orbital, but configuration doesn't. It's level, sublevel, and there's nothing in here about orbitals. And so with this, you treat these different sublevels and in summary form. There's nothing in this configuration that's going to tell you about orbitals. First element is hydrogen. Hydrogen on the periodic table is element number 1. That's because it has 1 proton. But if it's a neutral atom, then that means it also has 1 electron, correct? And as far as that scheme goes, when you put that 1 electron into this scheme, all atoms are built the same way. It's just a matter of where the electrons fall when you place them. The closest that that electron can get to the nucleus is right there. Lowest energy level, lowest energy sublevel that it can find. So hydrogen has its one electron on energy level 1 in an S sublevel. One electron present. So summarizing that diagram is on energy level 1, S sublevel, there's one electron there. Helium has 2 electrons, and the first one is going to be placed just exactly like hydrogen's would be, because they all fill by the same pattern. The second one, since there's room in that orbital for 2 electrons, the second one is going to go right down there with it. So we have a configuration like this. Energy level 1, S sublevel has 2 electrons. Lithium has 3 electrons. But this is not right. Why is this not right? That orbital fills at 2 electrons, right? All orbitals fill at 2 electrons. When you fill that up, then you got to move on to the next thing, which in this case would be your third electron. That's there. So 2s1. You've got 2 electrons on the 1s, and the third electron winds up in the 2s. You're filling from the bottom up. What's the configuration for beryllium? 1 is 2, 2 is 2. 4 electrons to place. This automatically is the first 3 because they have to go like every preceding element. And the fourth one would go right in there because there's still room there, correct? And that fills out the 2s. We filled what we had on level 1, we moved to level 2. We filled the 2s. If we keep going, which we will, then I guess we're going to start tapping into that 2p. The p sublevel that's on level 2. But do you see the pattern here, how that chart works? We're putting electrons in and filling from the bottom up. 2 electrons per orbital maximum. Yes?
Can you explain the lithium one again?
The lithium one? When you've got 3 electrons to place, only 2 of them can go in that 1s, because every orbital has an absolute limit of 2. So if you're putting that third one in, it cannot go to the 1s, and there's actually nothing else left on level 1. So the next closest thing it can do is the 2s. That's as close as it can get to the nucleus because the 1s is already full. It's kind of like dropping marbles down through one of those little machine things. They start to pile up, and that's what this is doing. That third electron piles up. The third and fourth electrons here pile up in the 2s. Go ahead.
Will it always feel like that? Like all the S's will be completely filled first, then all the P's, and all the D's, and all the F's?
No. Sorry.
That's just the pattern we were going in so far, so I was just curious if it's
No, the pattern that we're working on right now, well, you'll see. We'll modify it as we go. It would be nice if it stayed that easy. Now the next few elements. Five, 6, 7, 8, 9, 10 electrons respectively. At this point, even that 2s is full, correct? So now we got to start tapping into the 2p. Now, here's the thing about filling P, D, and F orbitals that we didn't have to worry about when we were doing S. And that's this fourth rule where each orbital can contain up to 2 electrons, but prefer not to. Because electrons being what they are, they're all negative, and negatives repel each other. And so it's better for them to spread out as much as they can, as much as it's possible, and not pair up unless it's absolutely necessary. So what's going to happen here? For boron, carbon, nitrogen, oxygen, fluorine, and neon, when we start to put electrons into these orbitals, we're going to put one over here, and then the second one is not going to go with it. Because if all 3 of these are equal energy, this would give you repulsion because they're sharing space, but this would not. As you go through putting these electrons in for boron through neon, this is the first one, the second one, the third one. You make one lap through putting them in individually. And then, if necessary, like for oxygen, fluorine, neon, you go back and you start to pair them off. So basically you're making 2 laps through. You go through the first lap placing them individually because that lessens the repulsion. It doesn't eliminate it, but it lessens it. And then the second lap you put them in pairs. That's important as far as how orbitals fill. That's not really important as far as electron configuration goes, because again, configuration tells you nothing about orbitals, right? But filling out the diagram, if this is the 1s, this is the 2s, this is the 2p, and let's just do oxygen over there. 8 electrons to be placed. Here's the first, here's the second, here's the third, here's the fourth. We're working our way up. 5th, 6th, 7th, 8th. So shorthand, the 1s has 2 electrons, the 2s has 2 electrons, and collectively that 2p has 4 electrons. Collectively, that 2p sublevel has 4 electrons in it. And notice that tells you nothing about which ones are paired, how many of them are paired. It's not trying to. It's just trying to tell you level and sublevel. Question about this. Using that diagram to get this for oxygen, first of all. Having that diagram to look at, is there a question about getting this? If there is, please ask. Or how to take this and summarize it into here. Question?
So basically, you're just taking one element and then filling it out through the whole thing. So it's
For however many electrons it has, you put in that many. Fill in from the bottom up.
What's the point? Just not, like, what is it like? How does that help?
That will help, I guess it'll be next week before we start making predictions with these. But as far as electrical charges, about why some elements, why sodium is a +1, but magnesium is a +2, all of that comes out of this kind of configuration. So once you see how the electrons are arranged, you can tell which ones are reactive and which ones aren't. And that allows you to predict what charges they're going to form, what kind of compounds they're going to make, and that sort of thing.
Sorry, that was the question.
Yeah, I mean, that's just a few days ahead of where that's where we're headed, definitely. You will be making those kinds of predictions. Just not today. Question about the pattern? All right. Using that pattern, write out the electron configuration for aluminum. And while we're at it, aluminum and argon. Do argon too. This is what you should have for aluminum. When you fill the 2s, you move to the 2p. Once you fill the 2p, you move to the 3s. And then after 3s, you move to 3p. And you just keep filling and filling and filling and working your way out. Is there a question about that for aluminum? When you've got it drafted out and you think you've got it right, one good thing to do to check yourself is add all these up and see if that comes out to be what it's supposed to be. Because that is your electron count. You're taking that 13 and distributing them out amongst your levels and sublevels. And so if you take those superscripts and they don't add up to 13, then you know you messed up. Question about that being the electron configuration for aluminum. Argon would have 18 electrons. And the configuration would look like this. Question about argon. Question about using this chart. Bad news is the system breaks down after argon. This works great. This little diagram works great for elements that are smaller than argon. And if you look at the periodic table, there's an awful lot of elements bigger than argon that this schedule's not going to work for. So we modify it a little. The next page gives you a more experimental diagram. What we were looking at was the theoretical structure, and it works fine for things that are small. But what's up here now is a more experimentally measured plot of where those energy levels fall. It's still level going up, energy level going up on the y-axis. Your sublevels, S, P, D, and F are in columns going left to right. And it's really the same pattern when you start out, that the first thing you fill is the 1s, then the next thing is the 2s, and then the next thing is the 2p, and so forth, just like what we did. But where it gets a little wonky is 3s, then 3p, and then what comes after 3p? 4s. And according to what we were just looking at, that's not supposed to happen. Because we were expecting to fill level 1, move to level 2, fill level 2, move to level 3, fill level 3, move to level 4, but it don't work like that. For whatever reason, the 4s comes in prematurely. You do the 3s, the 3p, then the 4s, and then you come back for the 3d. So things start to get a little bit out of sequence, and that's why the previous chart breaks down. And the further up you go, the uglier and uglier it gets. Because what comes after 6s? 4f. Then 5d, then 6p, then 7s. Yeah, that's complicated. But we got the chart, so we'll use the chart. Using that chart, draw out the configurations for potassium and arsenic. Using that chart. You don't have to memorize where those exceptions are because they're already coded into that chart for you. Just like before, you're checking in the electrons, you're filling from the bottom up, come up with these two configurations. what you should have for potassium. You fill up the 3P and then you move to the 4S, which is not what you would have predicted based on the previous diagram, but that is experimentally what happens. After the 3P, you move to the 4S. Is that what you got? Using this diagram, is that what you got? Arsenic then? You do get the 3D filled up, but you fill the 4S, then the 3D, that fills up at 10 electrons, and then you move to the 4P. And you're chucking them into the 4P when you run out. And so you end up with only 3 electrons in the 4P. Question? An S sublevel is always one orbital. And when that orbital gets full, then it's full at 2 electrons, correct? How many electrons can you put in a P sublevel?
6.
6. That's 2 electrons per orbital, correct? A P orbital can only hold 2 electrons, but a P sublevel can hold up to 6. D, 5 orbitals at 2 electrons each would be a maximum of 10, correct? And F?
14.
Apparently 14. 7 orbitals at 2 electrons each would be a maximum capacity of 14 for an F sublevel. The capacity of an F orbital is 2, like every other orbital. But the capacity, the total capacity of an F sublevel is 14. Question about that? Question about how to use this experimental diagram to get configurations. It does everything that the previous chart did, but it also allows you to go beyond argon because all these little glitches where things get out of sequence are on this chart. They were not on the previous one, but they're already on this one for you. Question about how to use this. All right.
Will you give us this?
No. But you don't have to memorize it either. You get something better. Even this breaks down when you get up to element 57. Oh, I'm sorry, 58. This chart works great up through element 58, but still, that's only about half the elements. What you get to help you is a periodic table. This one is in the notes. It looks a little different from your normal one because I've deliberately split it into sections. But all periodic tables are laid out like that. It's just that I put gaps in there so I could write in the margins. And notice that you've got a section that's 2 columns wide, a section that is 6 columns wide, a section that's 14 columns wide, 10 and 14. If you look at those 4 distinct sections, 2, 6, 10, and 14 columns in width, where have you seen 2, 6, 10, and 14 labeled? That's your sublevel capacities, correct? Not coincidence. The way that this is laid out is every element in this section has their last electrons in an S sublevel, and therefore it's called the S block, the S block of the periodic table, followed by the P block, the D block, and the F block. So when you're reading configurations off the periodic table, as far as level, sublevel, and the number of electrons present, you're reading off the horizontal row that it's on tells you the energy level. So this is energy level 1, 2, 3, 4, 5, etc. Energy level is determined by the horizontal row. The sub-level is determined by which section you're in. And then the superscript here is which column within that block. So graphically, row, block, and column will give you all the information you need for the configuration, and it works for all the elements. Not coincidence, because the periodic table was set up based on patterns of reactivity long before they even knew about electron configuration. But it falls out beautifully because the configuration is the reason they react the way they do. Lithium, sodium, potassium, rubidium, all those that are in column 1A as your alkali metals react similarly because they're built similarly. They were grouped based on how they react, but when you do the configurations, they're all very parallel, not coincidental. So starting back at the beginning with hydrogen and reading its configuration off the periodic table, we would go to where hydrogen is, we look at its atomic number, one electron to be found, and that one electron is on the first row of the S block and it's in the first column. Row, block, and column will give you the inventory here. Now the one alteration to this that's different than what's on a regular periodic table is helium. That's one modification, because usually, like the ones on the wall, helium's over here with the noble gases. But structurally, it's built more like beryllium and magnesium and calcium. So that one little alteration needs to be made, but otherwise things flow perfectly. Helium